In my last video, I had introduced Jablonski diagram to you. As you know, Jablonski diagram is a diagrammatic representation of the energy transformations that happen when a molecule absorbs light radiation. Now, to discuss more on Jablonski diagram, how we represent the energy transitions, etc., let us see how the energy levels are depicted. Now, this is the simple representation of the various energy levels of the electronic states or electronic energy states. Now here you can see S0, S1, S2, S3, they are the singlet electronic states. S0 stands for the ground state. Singlet means the electrons are in paired position. The spin of the electrons are anti-parallel. S1 is the singlet excited state 1, first excited state. S2 the second excited state. S3 the third singlet excited state, etc. You can see here smaller lines over here. Now these these bold lines represent the limits of each electronic energy state. Now from here to here you can have the singlet down state. From here to here you can have the singlet first excited state. From here to here the singlet second excited state, and so on. Now within each electronic state there are multiple vibrational states or vibronic energy states. Now you can see here V1, V2, V3, V4, V5. In every electronic state there is such vibrational energy levels too. Now this vibrational energy level can be further subdivided into rotational energy levels also, but in Jablonski diagram we do not go much into this detailed energy levels or intense levels in detail. Alright, now here you have the triplet excited state, first triplet excited state. This also has vibrational energy levels, and they are marked V0, V1, V2, etc. Now as the number of electronic energy state increases, or as the energy level of the electronic state increases, the difference in the energy becomes less. See here you can see the difference between the ground state and the first excited state in the singlet state is more than the first singlet excited state and second singlet excited state. And when you see the difference between the second singlet excited state and the third singlet excited state, the energy gap is still less. And eventually, as you move higher into the electronic level, the all the electronic levels tend to become continuous. Okay. Now, when these electronic levels become continuous, or when the energy gap between the electronic levels become less, there are chances that the vibrational energy levels of each excited state overlaps. Alright, we shall see what happens when the energy levels, when the energy gap between these excited states are less, or when overlapping of the electronic state and the vibrational energy levels of different excited state or different electronic states overlap. Now let us come to the absorption of light by the molecule. So when the molecule absorbs light, the electrons from the ground state moves on, gets excited, and goes on to the excited state. Now in this case this is a singlet excited state. Now the electron can move on to the higher vibrational levels of the singlet excited state, or it can limit, or it can be excited to the lowest vibrational level of the singlet excited state. It's possible. Now when the molecule or the electrons in the molecule gets excited, they will be unstable. Okay, their energy is high, so they will be unstable, and every system tries to attain stability by coming down to the ground state. Now this particular aspect, that is when the electrons or the molecules from the higher energy levels or higher excited electronic states come down to the ground electronic state, is called relaxation. Alright. Now relaxation process, there are different ways of relaxation. As we had discussed in the earlier video, there is radiative relaxation methods and non-radiative relaxation methods. Now, one way of relaxation is from the higher vibrational state, the molecule or the electrons come down to the lowest vibrational state of the same electronic state. Okay, so from the higher vibrational energy level of the electronic state to the lowest vibrational energy level of the same electronic state. Now that's one particular type of relaxation. Some amount of energy is lost. Okay, and this particular relaxation is called vibrational relaxation, and it is a non-radiative type of relaxation. That is, you do not, radiations are not emitted, but the vibrational relaxation occurs through collision transfer of energy from the excited molecule to other molecules. So there is no energy emission, but there will be transfer of energy from the excited molecule to other molecule. So vibrational relaxation is a non-radiative relaxation. Now another way of relaxation is from the lowest energy level of this excited state, the electrons, the molecules can come down to the lowest energy level of the ground state. So it is from one electronic state to another electronic state. Now this can happen from the higher vibrational energy state to the lowest ground state. So that's also possible. Now this particular relaxation mode will involve emission of radiation. That is, there will be emission of energy in the form of radiation. Now that energy will be less than the energy absorbed. And this particular phenomenon wherein the energy or radiation is emitted when electrons or molecules come down to the ground state from higher excited state, higher electronic state, is called fluorescence. Now the absorption, the time span or the time taken for absorption is very fast. It's about 10 to the power of minus 15 seconds. And vibrational relaxation is also very fast. It's around the same time span, between 10 to the power of minus 14 to 10 to the power of minus 11 seconds. While fluorescence is also a fast process, it takes the time span for fluorescence is between 10 to the power of 9 to minus 9 to 10 to the power of minus 7 seconds. Now in detail regarding fluorescence, we shall be discussing in the next video. So the fluorescence happens as a radiative transition from the S1 singlet excited state to the singlet ground state. Remember, the transition is between the same electronic state or the multiplicity singlet. Multiplicity is singlet, or the state is called singlet state. There is no change of the spin of the electrons. Now, another possibility of relaxation is And now from here, one more thing I forgot to mention to you. If ever the electrons or the molecule are coming down to the higher vibrational level of the ground state, then it will undergo vibrational relaxation from the higher vibrational energy level to the lowest vibrational energy level of the ground state. So here also vibrational relaxation is possible, and here also this is also non-radiative, while fluorescence is a radiative relaxation process. Another relaxation process is between different state, that is between singlet state and triplet state. Transition between singlet state and triplet state. Now that is called intersystem crossing. Okay, ISC, intersystem crossing. Now, during intersystem crossing, of course, this is also non-radiative relaxation. Now, we know that during intersystem crossing, the electrons move from the singlet state to the triplet state. Okay, so here, during this transition from the singlet state to the triplet state, the spin of the electron changes. Okay, the spin of the electron changes. Earlier, the electron over here had antiparallel spin to the electron in the ground state. Now, when it goes to the triplet state, the spin of the electron becomes parallel to the spin of the electron in the ground state. Now, intersystem crossing happens when the vibrational energy level of the singlet excited state overlap with the vibrational energy level of the triplet state. Okay, so when the vibrational energy level of the singlet excited state overlaps with the vibrational energy level of the triplet state, then intersystem crossing happens. Now, since it is a transition between the states of different multiplicity, intersystem crossing takes a bit time. It is slower than vibrational relaxation or fluorescence. Now, once intersystem crossing has happened, that is, once the electrons have reached the triplet state, it can again lose energy via vibrational relaxation from higher vibrational energy level of the triplet state to the lowest vibrational energy level of the triplet state, or this particular electron can move down to the ground state. When the electrons from the triplet state comes down to the ground state, there will be emission of radiation, and that particular process is called phosphorescence. So phosphorescence is the emission of radiation, or phosphorescence is a radiative relaxation mode between the triplet excited state and singlet ground state. Now, this phosphorescence is a slow process. It takes around 10 to the power of -4 to 10 to the power of -1 second. It is a slow process. Now, here also, if ever the molecule or the electron is in the higher vibrational state of the singlet ground state, it can undergo vibrational relaxation. Now, another relaxation mode is, suppose the molecule absorbs light and the electrons in the molecule gets excited, goes into the third or higher singlet excited state. Now, as I had told earlier, as the energy state increases, the energy gap between the different electronic states comes down or becomes lesser. and the chances of overlapping of the vibrational energy levels of one electronic state with the vibrational energy levels of the other excited state is possible. Now here in this electronic transition, the electron from the ground state has gone to the higher vibrational level of the second excited state. Now from here, another mode of relaxation what is possible is, from the second excited state, it will go on to the first excited state. So it is a sort of relaxation mode from the from higher electronic state to the next lower electronic state of the same multiplicity. That's important. Okay, this is between the electronic states of the same multiplicity. Now this is called internal conversion. Okay, so in internal conversion, what's happening? The electrons of higher vibrational level of a higher electronic state comes down to the next lower electronic state. So this is from S2 to the S1. It is also non-radiative mode of relaxation. All right. Now here the spin remains the same. Everything it's in the singlet state. It is a non-radiative relaxation, and the internal conversion is also very fast. It is almost taking the same lifespan or time span of our vibrational relaxation mode. It is the time span for internal conversion is also between 10 to the power of minus 14 to 10 to the power of minus 11 seconds. Alright, so from here, once the internal conversion has occurred, it can come down via the phosphorescence or vibrational relaxation. So remember, vibrational relaxation is the relaxation mode of electrons from higher vibrational energy level to the lowest vibrational energy level of the same electronic state, while internal conversion is from a higher vibrational energy level of a higher electronic state to a higher vibrational energy level of a lower electronic state. Alright, so that's internal conversion. So these are the various modes or ways in which the electrons or the molecules, when they absorb energy, the changes happening within the molecule. Now all these processes which we have discussed here are photophysical process of the photochemical process. Okay, photophysical process. There is no chemical change happening. There is only energy dissipation. Okay, losing of the absorbed energy in different ways. Now in detail about the fluorescence, vibrational relaxation, phosphorescence, etc. we shall discuss in the coming videos. So hope this Jablonski diagram is clear to you. It is the energy representation diagram of the various transitions happening when a molecule absorbs light during a photochemical reaction. Now the photochemical reaction usually happens over here during the interstitial, in the triplet state, and so we need to discuss more about that. So that is first interstitial crossing has to happen. The molecule or the electron has to go to triplet state, and it is from here that the chemical reactions take place, because over here the electron remain a bit more, the time span of the electron is more here because of the exchange energy, or since the energy of triplet state is less than that of the singlet state. We shall be discussing everything in detail in the coming videos. So try to draw this Jablonski diagram step by step and understand it. It's very easy. Alright, so thank you for watching the video. If you have any clarifications to be done, please contact me. Thank you.